I'm going to talk about equilibrium shifts. So, meaning we have some equilibrium reaction and it shifts in one direction or another. So, towards reactants or towards products in order to reach equilibrium or the state where the forward direction of the reaction and the reverse direction of the reaction are occurring at the same rates. Okay, so an equilibrium shift occurs in order to achieve equilibrium. Okay, so when we're talking about equilibrium shift, we want to know the reaction direction. So is it going in the forward direction or is it going in the reverse? Um, and basically, the reaction's always going to proceed in whatever direction is going to achieve equilibrium. So if it's not at equilibrium and it has too many reactants, it's going to go towards products to get to equilibrium. If it has too many products, then it's going to go towards reactants. Okay. And when I say if it has too many reactants or too many products, that's with respect to the that reaction's kind of ideal ratio of those things, which would be related to the equilibrium constant. Okay, so the equilibrium constant is determined based on a ratio of the product to reactant concentrations, and that tells us for a particular reaction what is naturally stable for it, kind of what's its happy place, what's its happy place of product to reactants, okay? And if it's not in its happy place, how does it get there? And that's what we're talking about. Now, how we actually figure that out is by comparing what we call the reaction quotient, which we symbolize as Q, to the equilibrium constant. So we compare those things. We compare the Q and K to identify which direction is our reaction going to go to get to equilibrium. And that's because the K tells us about where the reaction wants to be at equilibrium, whereas the Q actually tells us where we're at right now. Okay, so the Q actually could be written as an equation just like the K can be written as an equation. So if we look at kind of a generic reaction of A plus B going to C plus D, we write the K expression, the KEQ or just K, as the products over reactants, each raised to their stoichiometric coefficient. Okay. Well, the Q equation is exactly the same thing. Okay. So it's written exactly the same. The difference is what you're plugging into those equations. Okay. So if you take that equation and you plug in equilibrium values, so concentrations when the reaction is at equilibrium, what you're really calculating is the K value. But if you're just plugging in concentrations that you don't know if it's at equilibrium or not, you're really calculating Q. Okay. So K is for equilibrium, Q is for any time, even if you just don't know where you're at. And then you compare, your Q. If you don't know if you're at equilibrium, so you calculate Q by plugging in all those values, then you're going to compare the result to the known K for the reaction, okay? And if the Q equals K, that means, yes, your reaction is at equilibrium, okay? But if the Q is smaller than the actual K value for the reaction, then that means your reaction needs to shift towards products. Because if Q is too low, if you think about that ratio, it's products over reactants. And if it's too small, the way we make it bigger is by adding more stuff on top, meaning we add more products, right? We're not really adding something, we're shifting the reaction. And so the reaction shifts so that it can increase that ratio, which would be shifting towards products in that case. But if Q is greater than K at that instant, then the reaction is going to want to shift towards reactants because that is going to reduce that Q value. And it'll do that until the Q is equal to the K, okay? Until it reaches equilibrium. So you can actually predict which way a reaction is going to go if you know how much stuff you have at a certain point and you know the equilibrium constant of the reaction. Okay. And there's lots of reactions that there have been plenty of experiments done that the K value is known. Okay. And so then you use that known K value and you compare it to the Q for your situation. And then that tells you what's going to happen. So let's look at an example of this. So if we look at this reaction of N2O4 decomposing into NO2, the K value for this reaction, at least at some particular temperature, wasn't given here. It's not important at the moment. But the K value is 5.85 times 10 to the negative third. Then I say we have a reaction mixture that contains 0.0255 molar of NO2, and it contains 0.0331 molar of N2O4. And so from this info, I actually want you to first calculate the reaction quotient. Okay, so at this point, with these amounts of NO2 and N2O4, I want to know what's the reaction quotient. So first, you probably want to write the Q expression. So Q equals NO2 squared over N2O4. Okay. And so then I just need to plug in the stuff. So I'm going to plug in the NO2 value, which is 0.0255 molar, and that's squared. And then the N2O4 is 0.0331 molar. Okay. And then we're going to punch that in the calculator. So we take 0.0255 and square that, and then divide that by 0.0331. And that gives me 0.0196 for the Q. Now, just like the K, even though those concentrations have units, it doesn't matter what it results in, you drop the units. Okay, a Q value is unitless just like a K value is unitless. So this is my Q value. Okay, now what I want is to determine whether the reaction is going to proceed in the forward direction or the reverse direction in order to reach equilibrium, because it's not at equilibrium, right? These two values, they're not equal, and so it's not at equilibrium. And it may be helpful to just rewrite the K, right? The K value is 0.00585, right? And 0.00585 is not equal to 0.0196, right? And so really, your Q value is greater than the K value, right? So 0.0196 is greater than 0.00585. And so that means you have too much product, okay? When the Q is higher, you have too much product, too much stuff on the top of that fraction. So the reaction will shift left, okay? Or in the reverse direction, okay? That's the wording of the question, so I should say reverse direction. Okay. So that's just comparing then those numeric values. You're not going to do anything else with that number of Q. The Q is simply to compare, you know, is it higher or lower or equal than K? If it were equal, we were at equilibrium. If it had been less than K, then we'd shift towards products instead. But in this case, we're shifting towards the reactants to get to equilibrium. Okay, let's talk about one other thing related to shifts in equilibrium. Specifically, we're going to talk about Le Chatelier's principle. Now, what Le Chatelier's principle tells us is if you have a system at equilibrium and it's disrupted, so we do something to knock it out of equilibrium. So it's kind of happy and then we do something and now it's not happy anymore. And what's going to happen when you knock it out of equilibrium is the reaction on its own will shift in order to reestablish the equilibrium. Okay. So you can kick it out of its happy place, but then it's going to find its way right back there. Okay. Um, there's a lot of things we can do to some reaction at equilibrium that actually affects its equilibrium. Okay. Um, so different disturbances we can do is changing reactant concentrations, changing product concentrations. So if we change any one of the reactants or any one of the products, now it's not at equilibrium anymore. And the reaction is going to shift one direction or the other till it reestablishes equilibrium. Another thing, if you had a gas phase reaction, oh, excuse me. If you had a gas phase reaction, then actually changes in volume can affect it. We're not going to go into those specifics since we're not really talking about specifics of gases. But that would impact gas phase reactions. It won't affect others. Changes in temperature are another thing. And the reason changes in temperature would affect it is because changes in temperature affect the K value. So it'll increase or decrease the K value by changing the temperature, meaning the reaction then will need to reestablish equilibrium. Now, one thing that's really important that you realize is that a catalyst does not affect equilibrium. So a catalyst is something that speeds up the rate of a reaction. And so sometimes people think that that affects equilibrium. It does not. It affects how fast a reaction reaches equilibrium. Okay, so a catalyst is going to speed up how fast one direction or the other of the reaction goes. Actually, it'll speed up both, I guess, but it'll significantly speed up one of them more so, really. But it doesn't affect the equilibrium. Okay, so the equilibrium constant still holds true. And so, yeah, a catalyst can't change that. A catalyst only speeds up the reaction, thus reaches equilibrium faster. That's it. Okay, so let's focus on the concentration changes. Okay, this is the most basic manipulation to equilibrium. Temperature isn't too bad, but we're not going to go more in depth of that. We're definitely not going to talk about pressure though. Temperature, it's all related to whether it's an endothermic or exothermic reaction. That's why a K value would change because of temperature changes. But we're not going to talk about that in any more depth. So we'll focus on concentration changes. And the way you change the concentration of something is by adding more or less of it or taking some away, right? It's easier to add. So usually you're adding something. But I guess you could find a way to take some particles out of this. But if we add a substance, then your equilibrium is always going to shift away from that added substance. Okay, so if you add more of something, now it throws off your ratio. Okay, so initially your ratio was where it needed to be, but if you add something, the reaction needs to try to get rid of some of it because the ratio is not right anymore. Whereas the opposite would be true if you remove something. If you remove something, now that ratio is also messed up, and the reaction needs to try to replenish that. So the reaction would shift towards the removed substance. So no matter what, it's all tied to that equilibrium ratio of products to reactants. If you take something away, it needs to put it back, which it can't just put that back by shifting the reaction. It actually changes everything at that point. Same with if you remove something or if you add something, it needs to get rid of it. Okay. So in reality, your new equilibrium amounts when you add or remove something are never the same as what you started with. So when we say the reaction shifts to reestablish equilibrium, it doesn't mean to get back to the exact same amounts of things. It means to get back to the ratio that's needed, the K expressions ratio. Okay. Um, so the same essentially proportions of products to reactants, but it doesn't have to be the same amounts, okay? Which it won't if you added or removed something. So if you add something, that substance is always going to be higher. Now, when you add it, the reaction shifts away from it, but, so you added some, and right after you add some, it's going to decrease a little, but it will never decrease back down to before you added that. Okay. So anything added is always going to end up at a higher amount than what you started with. Okay. Whereas if instead you removed something, that removed substance can never get back to what it started as, because the reaction will shift towards it, but it can't shift towards it to replenish all of it. It can only shift towards it until it reachieves its ratio, okay, that makes it equal to the or the equilibrium constant. Now, everything else in the reaction is how it changes is going to depend on where the reaction shifts. If the reaction shifts towards where the substance is, that substance increases. If it shifts away from it, it decreases that substance. Okay. Okay. So, like I said, we're only going to focus on the concentration changes with respect to Le Chatelier's principle. Okay. So let's look at a couple of examples, and hopefully, if this doesn't already make sense, it'll make a little more sense to you. So here we've got this reaction, and we say that we've got this reaction and we have it at equilibrium. And I want to know if it's already at equilibrium and then I add some BRNO, what's going to happen? So I'm adding some of the reactant. If I add some of that, the reaction needs to shift away and get rid of some of it. Okay, so if I add some, now the reactant part of my ratio is too large. And so I need to take some of that away and give some to the product part to re-achieve my K ratio. Okay, so this is going to cause the reaction to shift. Usually I'd just say shift right. Okay, or shift towards products. Okay. Now the next one I say, what's the effect of adding Br2 to the reaction mixture? So Br2 is a product. So that means now my ratio has too much stuff on the top. So it needs to shift away from that. It needs to shift towards reactants to reestablish that proper ratio. So in this case, it's going to shift to the left. Okay, so it's always going to shift away from things that are added. Now, if we remove NO, NO is a product. And if we remove something, the reaction needs to replenish it. And so in order to replenish NO, it needs to shift to products or shift to the right. Okay. And then let's see. Oh, whoops, I didn't realize I do have a volume one here. Let's ignore this because we're not talking in depth about gases. So I'm just gonna not talk about that one, because that one we'd need to go a little more in depth about how gases work. So we'll stick with just those three on this one. Let's go to the next one. Okay. Oh, maybe. There we go. Okay, so we have another reaction, but now I say, how does each of the following changes affect the NH3 at equilibrium? Okay, so instead of what direction does the reaction shift? I'm asking, how does it impact this substance? And so I want to know, how does it impact NH3? Okay. Probably because we're probably doing this reaction because we want to produce NH3, right? And so I want to know, am I going to get more NH3? Am I going to get less NH3? So here, first I say increase the concentration of H2O. So if I increase the concentration of H2O, that's a reactant, and so it's going to need to shift away from that, okay? So what's going to happen is now it's going to shift towards the NH3, so that will increase the NH3, okay? Because the reaction will then shift towards it to get rid of some of that H2O that was added. And then if we decrease O2, well, O2 is a product, so if I start removing that O2, then the reaction is going to need to replenish it to reestablish equilibrium. And so this also will increase the NH3. Okay. Now, if we add a catalyst, what does that do to the NH3? Well, in that case, there would be no change. And that's because a catalyst is only going to speed up how fast the reaction goes, so how fast we get to equilibrium. So if it's already at equilibrium and then you add a catalyst, there's really no point. It's not going to do anything. It'll speed up, I guess, the interchange between reactants and products, but you're still going to have a constant amount of them. Okay. And so this is kind of really a little bit more of a practical way to think about Le Chatelier's principle. Usually you have some goal in mind. So you say want NH3 and you're trying to come up with ideas of how you could get more. Okay, so say this reaction, you weren't given a K value, but let's say this reaction has a really low K value. That would mean that the reaction favors reactants. If that were the case here and we wanted NH3, that wouldn't be good because that would mean we're not getting much, okay? And so if we were to add in more H2O, then that tricks the reaction into forming more NH3. So that's one way we could get more product, okay? Or we could find a way, find something that will pull the O2 out of there, okay? So something that'll absorb specifically O2 gas. And then that will trick the reaction into forming more products, okay? So understanding Le Chatelier's principle is one way that you could manipulate the results of a reaction. So you can trick the system into giving you what you want, okay, by changing concentrations of things. But if you don't understand Le Chatelier's principle, you don't know what you could change to fix this, right? I guess you can always do trial and error, but it's nice to just be able to look at it and be like, oh, well, obviously I can just add some more NO, or I can just add some more H2O and it'll give me more product, okay? And so you can find ways to manipulate the equilibrium if you understand Le Chatelier's principle.